specifically, what is kudzu? It's a perennial leguminous vine that is native to China and Japan, has a very large taproot, and they have very high carbohydrate reserves. Now, this is one thing that most people don't know about kudzu, because if you live in the southeast, primarily you just see this, which is because kudzu has a very rapid growth rate. It's 29 to 30 meters per growing season. So every season, each plant pushes out 29 to 30 meters of growth. Now, the real problem with this, as far as everybody's concerned, is a single root crown can produce as many as 30 vines. That's a lot of growth. It has a relatively high protein concentration. It's 23.7%. That's fairly impressive. It's also completely edible. You can eat the leaves, the stems, the roots, everything. It's actually a medicinal plant. Chinese herbal medicine lists kudzu as one of its top medicinal plants. It's a good source of trace minerals and the B and D vitamins. Now, everybody knows vitamin D, vitamin B. We need that, need more of it. D vitamin, especially with people being inside more and more, less D vitamin because you normally get it with exposure to sunlight. Trace minerals are good. It's low in fat and calories, which is fairly popular these days. It's also a legume. It's a nitrogen fixer. Now, the reason it was introduced to the southeast, this is a key point, it's a stabilizer. It grows out, stabilizes the soil, stabilizes the slopes. Does very well at this. The problem is there's not a whole lot of stuff that eats it. Cattle will eat it, and they like it, but it has to be introduced to them. It's not something they eat naturally. I actually took a moment to talk to an old gentleman who raises cattle in Etowah County, and he has no kudzu problem. He has 20 to 30 acres cattle. It's all kudzu. Doesn't have an overgrowth problem because the cattle eat it. So it's very good as a feed, and you can use the stem tissue and make fiber for cloth as well. That's just another little trick that it has. The starch is used to make noodles. It actually works quite well for that. Now, this picture, however, is not root that has been used for noodles. This picture is actually dried root that is going to be used as an herbal medication. It works quite well for fevers and other such diseases and treatments. It's also, according to more recent literature, a very good probable treatment for alcoholism. Something in the roots treats the alcoholism. It reduces the desire for alcohol and reduces the problems. That's only emerging. They're in animal testing right now, but that's a very handy thing since these roots can get upwards of 400 pounds. The largest on record is 512, and I believe that was in the state of Georgia. Now, we looked at antioxidants primarily. What is an antioxidant? They prevent some oxidation chain reactions by removing the free radicals, and they do this either by slowing down or stopping the procedure and preventing other molecules from being oxidized, or by interrupting the oxidation of other molecules by being oxidized themselves. I have the structure of several of our antioxidants that we looked at. Let's see slightly better pictures as we go. The first group that we looked at was a major group, the total polyphenols, and they're characterized by multiple phenol groups on a molecule. They are divided into three major groups: tannins, lignans, and flavonoids. We looked, again, primarily at the polyphenols and then calculated the flavonoids, and then we looked at a major polyphenol and a major flavonoid. These are the anthocyanins, and they are water-soluble vacuolar pigments that can be red, purple, or blue according to pH. Purple is a basic pigment, blue is more neutral, and red is more acidic. As you can see here, the purple corn, which is reputed to be the highest in anthocyanin concentration, is bright purple. Now they go from this brilliant purple color, or bright red or blue, to kind of a rust brown color after they're oxidized. The second group we looked at was the carotenoids. They are organic pigments. They occur in the chloroplast, chromoplast, and plastids of plants. There are over 600 known carotenoids. The most important one is carotene and beta carotene. These are very important. They're the yellow and red and orange pigments that you can see in here. And the nice thing for plants, this is their major role in plants, and algae, or one of them, is they absorb light for photosynthesis and they protect against photooxidative damage. So they're a secondary photosynthetic pigment as well. Part one, this was the first half. This was, as Dr. Al-Hamdani mentioned, I finished this up right as I was entering the program for my master's thesis. This is the evaluation and comparison of selected antioxidant concentrations in kudzu and 3 common food sources. Here we have kudzu. Here we have spinach. Everybody knows spinach. Up on the top here, this is actually a lab-grown shiitake mushroom that Dr. Al-Hamdani and myself grew in the lab. That's a notebook in the back, and that is for reference. That is, I am holding it. That's a fairly large mushroom. It weighed 91 grams. And then here we finished up. Our fourth is nori seaweed. It's Porphyria tenera. Primarily, you see it primarily in the States dried as a sushi wrapper. It's also being used more and more as a raw vegetable. So it's becoming more and more popular because it's easy to obtain. And the reason we looked at this was because everybody knows that we're having a large increase in the human population. You see on the news, it goes up, we've got more people, less food. This is aggravated by multiple issues, but you know, in certain countries in the world, they're starving. They don't even have enough rice to give a whole family a cup of rice in some places. So we were looking for something that could be dietary beneficial. Also, antioxidants have become more and more popular. We're getting more and more problems with poor diet. So high in antioxidant has become a good thing because it will slow down some of the damage that we get. We determined selected antioxidants and compared them to spinach, nori seaweed, and the shiitake mushroom. We sampled kudzu samples. The leaves were taken, fresh samples, and brought back to the lab, and immediately sampled for our test purposes. And we purchased fresh spinach, seaweed, and shiitake mushrooms from the local grocery store. Analyzed total phenolics were analyzed using Singleton and Rossi 1965, which is a colorimetric method. You homogenize the tissue on with a mortar and pestle using liquid nitrogen, it lyses the cells, you extract it with methanol, 3 grams of methanol per 100 mils, extract out everything, and then back extract and make sure you've got all the compounds that you're interested in, and then analyze it. It's a phenol heavy metal reagent that starts off a light green color, and as the concentration of polyphenols increases, it goes to a darker green to black. And it can get to the point where the differences are not detectable, the color differences are not detectable to the human eye. The flavonoids are calculated very easily from this test because 84% of the material that is detected by the reagent are the flavonoids. The other 16% are other polyphenols. Anthocyanin was done using an acidified methanol reagent method, and it's colorimetric as well. And then our third procedure was beta-carotene using the beta-carotene linoleic bleaching assay, which is a little different. It's also a colorimetric method, but you use a known volume of beta-carotene to determine the range, and then expose your treatment sample to the same reactive ingredients to determine where it stands against your known volume. So here we have the concentration of total polyphenols and flavonoids in kudzu compared to the concentrations found in spinach, seaweed, and the shiitake mushroom. Now, here we can see that kudzu has 5.9, and then it drops by over half to 2.7 in spinach, and then to 1.3 and 0.8 milligrams per gram for the seaweed and the shiitake respectively. The last two, the seaweed and the shiitake, were not significantly different from each other. And spinach, which is, according to the literature, one of the highest concentrations of polyphenols, it has 13 polyphenols that are identified that are presumed to be anti-cancer or anti-tumor properties, which means it has very good polyphenols. And then to come in and see that kudzu has 2.5 times the total polyphenols that spinach has was quite impressive. And again, the flavonoids are a calculation, and they follow the same pattern. Then we move on to anthocyanin. Remember, this is the water-soluble pigment. Was 37.5 micrograms per gram fresh weight in kudzu, dropped to 19.75 and 19.7 in spinach and the nori seaweed, and then dropped a large amount to the 0.85 in the shiitake mushroom. Now, there is one thing about the shiitake mushroom. It has been hypothesized in the literature that the mushrooms do not produce the anthocyanin pigment themselves. It has actually, according to the USDA and several other places, it's more what they're fed. So that has been patented. Feeding them purple corn was patented last year by a group out of California, and it has shown an increase in this concentration. Now, the beta-carotene showed a different pattern from the other two. Every measurement, kudzu, the spinach, the seaweed, the shiitake mushroom, they're all statistically different from each other. You can see the drop from 17.25 to 9.6, which is about 1.8 times higher in kudzu than it is in spinach. Then it drops to over 5.5 times lower in the seaweed. And here is the largest, this last row right here is the largest difference we saw in the whole study. Kudzu has 250 times the concentration of beta-carotene that the shiitake mushroom has. That's a large difference. When we look at the nutritional antioxidant value, it's 2.5 times polyphenols and flavonoids, and 3.75 times and 6.39 times when compared to the other two, respectively. In conclusion, this sums up the fact that we found much higher antioxidant concentrations of all three in kudzu than the other sources that we tested. which was a little bit, to be honest, was a little bit of a shock to me because I was expecting spinach to come out highest. Now part 2, I have been working on this since after I entered the master's program, since we discovered that kudzu has very good nutritional antioxidant values and the literature supports that it has very good beneficial properties. We were looking at the drought tolerance of kudzu because drought stress affects a large portion of the world. According to the last UN study, 1/3 of the world's agriculture is affected by drought stress. That's a very large portion, and that is in irrigated and rain-fed agricultural systems across the globe. It's followed and nearly tied by salt stress, but that's a different topic. It aggravates multiple problems such as soil erosion because drought stress reduces your plant growth, which means that the drought-tolerant plants that do grow do not have enough mass and enough vegetative material to cover the soil. So it aggravates soil erosion, which leads to poor soil, which leads to more reduction in growth. So we looked at the drought stress using polyethylene glycol-induced water stress or drought stress in a hydroponic medium. One major reason for the hydroponic media is if you go back and look, and if you can look online, it's a quick Google search, Alabama kudzu is considered an invasive species and it is against federal law to plant it in the field. It has to be under controlled conditions in a greenhouse and all the specimens have to be destroyed. We looked at selected criteria from all of our plants, including the osmotic adjustment and the antioxidant response. Now, kudzu, this goes back to what we talked about in the introduction. The main reason that kudzu is so hard to get rid of is it has very thick sclerenchyma tissue on the cells. Has very, very thick, or on the seeds. They're very, very thick. Takes very long amounts of time to break down that tissue and these seeds to germinate. So what you have to do to germinate them in the lab is scarify them. You introduce the seeds to a little sulfuric acid, spin it on a stir plate, it melts the thick tissue off, you drain the acid off, wash the seeds with distilled water, and plant them. They germinate quite readily after this, and after 3 weeks, we transfer them into glass containers of our Hogland solution, which is our hydroponic media. They were allowed to acclimate for 1 week, get them used to their changing environment so they're not stressed before they were assigned to either a treatment group or the control group. These are from my first set of kudzu plants, and you can see that they're quite healthy. These are 3 weeks old after they've germinated. These are 3-week seedlings. And we germinated about 3 times the number of seeds that we actually needed because we picked the healthiest seedlings to transplant. So these are where they're being separated and transplanted, and then this is where they've been transplanted, and this is actually right before they're divided up for treatment. You can see how the plants are all fairly uniform. It reduces the error in the experiment if your plants are uniform, so that you don't have a kudzu plant that is, 3 or 4 feet long with vines versus a kudzu plant similar to this plant right here. And here's just a quick snapshot. Some of our plants growing up. This is Kristen, who most of you may or may not have met. She graduated in August. Her research was on kudzu with lead, and we worked together a lot with the plants and transplanting them to the Hogland solution because we both used similar media. And This is just a nice snapshot, and this is everybody actually right before transplant, and then these are some under treatment. The reason we use polyethylene glycol, there are two ways to do it commonly in the literature, and polyethylene glycol is one of the main ways. It's one of the two. It's a long-chain, non-penetrating, high molecular weight polymer. It's been used for years because it's very easy to use and it's very stable. It's very effective at dissolving in water and binding water and introducing osmotic stress and drought stress. We used 8,000, which has been the standard since the 70s. It replaced PEG 6,000. That replacement is more of a manufacturer's name change. Instead of being PEG 6,000, it was relabeled PEG 8,000 because the molecular weight was off. So this is the molecular formula for it. The only problem with using PEG in hydroponic media is it induces anoxia to the media. It prevents water from getting in, or prevents oxygen from getting into the hydroponic media. The solution to this is very easy. Actually, the manufacturer recommends when you use PEG in anything to bubble the solution if you're doing it for testing. So we simply connected all of our hydroponic media, all the glass containers, connected to air lines. They were bubbled constantly throughout the 14-day treatment. After 14 days, treatment was halted and samples were taken for testing. Our treatments were, of course, our control was Hogland solution with no polyethylene glycol, and our first treatment was 52 grams per liter, followed by 79.5 grams per liter and 101 grams per liter polyethylene glycol. Now, the reason these concentrations were chosen, in 1983, a man by the name of Michael sat down and analyzed polyethylene glycol in solutions like Hogland solution for the water potential and what concentration was needed to give you the water potential that you wanted, or how to calculate your water potential if you know your temperature and your concentration. So we simply used the formula, calculated it for our greenhouse condition temperature and the water potential that we wanted, and it very easily gives you the number of grams that you need per liter of polyethylene glycol to induce that treatment and that stress. Here's a slightly better picture. You can see the air lines going into the containers to bubble the solution. Primarily, we were interested, as I said, in the osmotic potential, or the osmotic adjustment, and the antioxidant growth, or the antioxidant levels of the kudzu. However, one of the major effects of drought stress is on the growth. After treatment, after the samples were taken for the other tests, we severed the plant, the shoots from the root, at the root crown level, and they were oven dried to give us a dry weight to determine how much was affected by the treatment. We also looked at the shoot over the root to see if there was more effect to either one, or if there was more of an effect overall. And then we measured the water potential and the osmotic potential using the vapor pressure osmometer. Now this is very important because water potential is one of the main ways to determine the adjustment of the plant to the stress. The water potential in a plant is always negative. Always, always, always negative. And this is a good thing because it allows it to take up water from its environment. As the environment becomes more and more stressed and the water potential in the environment goes down, the plant will decrease further to allow it to continue to take up water. And the water potential is also affected by the osmotic potential. It contributes negatively to the water potential. Pressure potential contributes positively to the water potential value, but we didn't look, pressure potential was not calculated in these results. It gives us the water potential. You can see here we took the leaf tissue, smashed it in the French press, and then took the solute with a micropipetter and added it to the disc, used a vapor pressure osmometer to determine the water and osmotic potential values, and then we analyzed the photosynthetic pigments. We used 0.05 grams of leaf tissue taken from the same leaf, a leaf in the same position on every plant. Took 0.05 grams of leaf tissue and placed it in 5 mils of DMF in dimethylformamide for 36 hours. This is a bleaching agent. It extracts all of the photosynthetic pigments, chlorophyll A, the chlorophyll B, and the carotenoids, bleaches it all out of the leaf tissue. You use the photospectrophotometer to measure it after 36 hours using a cuvette. There are 2 wavelengths, the optimum wavelength for chlorophyll A and chlorophyll B that are used in the method of calculating chlorophyll, and then the carotene is calculated at a different wavelength. After that, we measured the total polyphenols, 3 grams of leaf tissue, same as the earlier procedure, hit it with liquid nitrogen, homogenize it in mortar and pestle, add it to the methanol, extract it, evaporate off the methanol, and then analyze it using the colorimetric method to determine the concentrations of the total polyphenols. Our results here, now keep in mind the 2 values on this table, they are negative numbers. The units are negative megapascals. So even though the numbers look positive, they are actually negative. Our control group was minus 0.83 megapascals for water potential and minus 0.75 megapascals for the osmotic potential. And you can see a significant decrease from the control to the first treatment group, which is 52 grams per liter. It's also our minus 0.5 megapascals. You can see that these values are more negative than the environmental condition they were grown in. And as you move down, 79.5 grams per liter is more negative than the environment is in, because it was at minus 1 megapascal. It's at minus 1.06, nearly minus 1.07. And then the 101, which is our minus 1.5, is minus 1.514. It's slightly more negative than the environment that it's in. And as you go down the water potentials, the osmotic potentials also decrease. Now, there is one thing about this table, the way it's analyzed. This was at the most conservative that I could go for calling a significant difference in these treatments. Next, the treatments induced a significant decrease in both the shoot and the root. You can kind of see here, this is one of the leaves from one of our treatments. This is at about 5 days. The leaves started to curl. That's in response to the changing water relation in the plant and is common in many species. Now here, our control is 14.6 grams for the shoot and 2.9 grams for the root. It drops by nearly half in the first treatment to 7.3, and that's a fairly impressive drop. And here, if you'll notice, this 3.97, the most severe reduction to growth was seen in the second treatment group, the mid-level stress, when compared to the first or the third treatment group, which showed a slight rebound. It's not a significant rebound, but there is a rebound. Now, if you look over here at the root, you can see that there's more of a rebound in the there's a more significant rebound in the root than in the shoot. And this is because it's looking for water. Growing out its root at the sacrifice of its shoots is actually not a bad thing as far as it's concerned, because if it can find water, then it can start regrowing everything else. And over here we have a ratio of the comparison. You can see that it drops. Here there's no significant difference between the two treatment groups. The difference is significant in the roots. However, the recovery was not enough for there to be a significant difference overall between the last two treatment groups. And here's just a visual. This is my control plant at 14 days. And this is one of the high-level stress groups at 14 days. You can see that there is a reduction in the growth because of the treatment. And here's the roots. You can see that the roots on the Kudzu, the control plant, are very large. There are lots of roots, and they're very long. There is a reduction in the size and number of roots. However, you can't really tell it from here, but the root actually does continue down through the table. I couldn't get a very good picture of it from where I was at, because there are several that are slightly longer. There's about 5 that are longer than everybody else. Now onto the chlorophyll A, chlorophyll B, and the carotenoids. Chlorophyll A in all of the treatment groups was higher than chlorophyll B, which is to be expected. You see the same pattern that we saw, have a decrease from 32 to 29. The most significant decrease is again in the second treatment, where it decreases to 21 and then rebounds to 24.9 in the third group. Chlorophyll B follows the same pattern. However, the ratio between the two, the control is not significantly different from the first group. However, the other two treatments are significantly different from the control, and the first treatment is not significantly different from the other treatments. Now, the odd one was carotenoid on the end here. It's a secondary photosynthetic pigment, and it's also an antioxidant molecule. However, there was no significant difference as far as any of the treatments in the control were concerned. The treatment had no significant effect on any of them. There are variation. You do see a reduction, or you do see an increase. The reduction is in the controls levels, but it's not significant. Even though the numbers are higher, they are not high enough to be significantly different. Finally, we move on to the total polyphenols. Here in the control, these are our hydroponic controls with no polyethylene glycol. And when you compare the value found in the hydroponic control versus the values from the first study from field samples, they're not different. There's actually a little bit of overlap in the levels. So they're very close to each other, so the hydroponics did not seem to have an effect on the total polyphenols. It increases significantly. The second column is the first treatment, 52 grams per liter. And it increases again in the second treatment, and then the highest increase is seen in the third treatment, 101 grams per liter, which is the very stressed plant. If you look back at the, if you remember the growth pictures, it was a very stressed plant, and these levels are much higher in that group than they are in the control. In conclusion, the water stress treatments caused a reduction in plant growth and the chlorophyll concentrations. which was most likely caused by free radicals induced by the water stress and the alteration of the water relations in the plant. Because the water relations changed in response to the treatment, it affected large amounts of what was going on in the plant. And the extent to which it can avoid the drought stress can be determined primarily through the formation of its antioxidant compounds and the osmotic adjustment, and they both were significantly increased in response to the stress treatment. The pattern was actually very similar. What we saw was very similar to what was found in other plants, especially the total phenolics and the osmotic adjustment. It was closer in comparison studies between drought-tolerant and drought-sensitive varieties. It was almost identical to drought-tolerant varieties of rice, wheat, and pine, according to the published literature. And this was from papers all over the world, including some done in the U.S., and some done internationally, and some done as collaborations. So there's a lot of data to support that this pattern is more common with a drought-tolerant variety. And with that, that's the end of the data. I would like to thank my committee chair, Dr. Safaa Al-Hamdani, for all of his help and guidance. And I would also like to thank Dr. Miji Tabahamasu and Dr. James Rayburn for being on my committee and for all of their guidance and help throughout all of this. I would especially like to thank Dr. Chris Murdoch. Dr. Murdoch was actually the first person who got me in the lab and let me do some research. So I really have to thank Dr. Murdoch for that, and I have to thank him for helping me get to where I am today. Thank you, Dr. Murdoch. And Dr. Valair, I really would like to thank you for your help, especially with getting this. I would like to thank Jenny Lee and Samantha for their help in the lab. A lot of the help with the photosynthetic measurements, a lot of those, Jenny Lee helped me with that. She was here very late, several days to help with that. Samantha's helped in the lab for years. I would like to thank the faculty of the Department of Biology and the university. And most importantly, I would like to thank all of you for coming. Any questions? Dr. Meade.
What happens during the recovery phase? Do they recover? And
We didn't let them go into recovery. We measured it at the end of stress. They probably would see a recovery. A lot of plants do, though some species do not. It varies on plant species. That would be more of a next project for somebody else to continue the research and look and see what happens. Dr. Blair.
Could the age of collection of the spinach cause a difference between the numbers you were seeing? Because you were collecting the kudzu fresh, and the spinach, who knows how long it'd been collected.
I tried to get as fresh as possible, but when we were doing it the first time, the timing was off to get fresh spinach, so it was not able to get it freshly harvested. I checked that in the literature, and there are several papers that use bagged spinach in comparison to regular spinach and didn't see a difference. So,
Do we have a French press on campus?
Dr. Al-Hamdani has 2 of them. Yeah, it was actually in the picture. It wasn't very clear, but it's in there. Any other questions? Brett?
Did you actually eat some kudzu? You said it's all edible.
I have actually tried it now. They talked me into it.
Is it good?
Do you like turnip greens?
No.
Then you're probably like, it's a little bitter for my taste. Though, oddly enough, in Georgia, they deep fry it, put it in with sugar. They make jellies, jams. You can stew it like turnip greens. I think the favorite one that I have is I tried some of the noodles. They're actually not real bad.
I suppose if you put enough salt and salad dressing on anything.
Yeah, you can eat spinach with enough salt and salad dressing. Any other questions? Dr. Triplett.
Yes, with all the great potential of this plant, are you aware of any programs testing it, for example, PI stations or in the U.S.? Doing crop tests with this species?
There are several, mostly in California. Actually, the mention has been made to do it in Oklahoma as well. I don't know how much that's going to be done. But they're not looking at it for nutritional value. It's being batted around as a provisional biofuel source because of the large biomass and the fact that it's very easy to grow. We were looking at it from a more nutritional point because it's also very easy to grow, very easy to maintain. You plant it and it goes. It takes care of itself, which would make it very beneficial in areas where you don't have a lot of farming experience or anything like that, or it's not the expertise is not available or the equipment's not available to maintain it. Be quite well. I think it has been brought up in several places outside. I'm not 100% certain on that, so I don't really know as far as nutritionally. Any other questions?
Well, thank you very much. Oh, go ahead, go ahead.
So, I'm not sure, I don't think is it more drought resistant than most plants? Is it like better growing in areas that are prone to drought stress?
It actually survives the third stress treatment that we gave it. Rice will not do that. Our third stress treatment will kill rice, even the drought tolerant variety, after 14 days. So it's a little, as far as it's more drought tolerant than some species, but it's on a per species basis. It could be used primarily could be used overseas as an alternative crop in areas that have either poor soil or seasonal drought stresses. Egypt would be a good one, several places in the Middle East, because it does very well. And in areas like that, it could be used, you don't have to use it for human consumption, you could use it for livestock feed, but it's edible for humans, and that might make a difference in some places. That's actually, we were considering it more for overseas than in the US, but it's viable either way. We have a lot of it in the Southeast, and it's just a shame that everybody's interest goes into how to kill it, not what to do with what we've already got.
Well, thank you very much.